we're going to wrap up 2.1 here with an application problem that involves a table of data. And truthfully speaking, a lot of concepts we talk about in calculus are out there and they get used a lot of times by people who maybe don't think of themselves as mathematicians or people that even know much about calculus. Because they're not working with, life doesn't come with a function s of t equals 12t squared plus t, right? A lot of times, math happens a lot more with data and maybe something like this, a table of some data values. So let's take a look at this one. It says a tank is filled with 80 liters of water at 7 a.m. and that's going to serve as our t equals 0. And you can see that's the first data point in our table, by the way. Over the next 12 hours, so you can see the last data point there is 12 at t equals 12. The water is continuously used. The table is giving the amount of water in the tank, so the amount of water remaining at that specified time. So part A, so you have your table of values there. Part A says use the table to approximate a prime of 9 and do that by averaging the best two approximations. So remember, a prime is our notation for the derivative, right? So in a world where potentially I might have been given a function to start, like some sort of a of t function, what might I have started with? I mean, if I was thinking about doing a prime of 9, I might have said, oh, well, let's think about taking the limit as, t approaches 9 of this a of t function minus a of 9 all divided by t minus 9. I mean, that's our definition of the derivative, or, in this case, the rate of change at 9. But the problem is I don't have an a of t function, right? And this is how life tends to work a lot more often when it comes to data. So I don't have that kind of information here. So what we want to do is we want to go back to realize, first of all, we are approximating, and we approximate, we're going to, like, our best two approximations here are going to involve looking at the rate of change, the average rate of change on the two intervals that are closest to 9. So here's what we're going to do. We're going to say first, let's look at finding what would be the average rate of change on the interval from 7 to 9. And then we can also look at what would be the average rate of change on the interval from 9 to 12. So, I don't know why that's not supposed to be a open parenthesis. I just got lazy. So that's what we're looking at here. So initially we're saying, well, I could look at what happens from 7 to 9 and figure out what's that average rate of change. And then I could also look at what happens from 9 to 12, and I could figure out that rate of change. And so those are the two things that we're doing here. Okay, so average rate of change is simply, it's really slope, right? It's change in y over change in x. It's looking at what's the change in the outputs. So the change in a of 9 minus a of 7 divided by the change in the inputs. And I wouldn't even expect that you would write that out. We would probably just go to saying it's the change in the output values divided by the change in the input values. So what do we have here? We have negative 6 over 2, so we have negative 3. Okay, let's do the same thing, focusing on the interval from 9 to 12. So again, what are we doing? We're taking a of 12 minus a of 9, change in outputs over change in inputs, just average rate of change. So probably just starting immediately with 50 minus 54, again, over 12 minus 9. So in this case, I'm going to have my negative 4 thirds. So these are kind of the best two approximations that I can make for the rate of change around 9. So now what we're going to do is we are going to average those two approximations. So we're going to average these best two approximations that we have here. So let's go ahead and do that. So simply adding up -3 plus our -1 1/3, right? -4 thirds. Just adding those up and dividing by 2. So -3 over 1 multiplied by 3 over 3, that's like -9 thirds. Plus -4 thirds would really be like -13 thirds. And dividing by 2 is like multiplying by 1/2. And so we get -13 sixths. Or of course that is -2 1/6. So this is our final answer. That's our approximation. So this is our approximation for a prime of 9 by averaging the two best approximations that we can make from this table of values. All right, so that was all very formulaic, if you will. We haven't even put a label on this yet. So I want us to interpret this, including appropriate units. And so let's go ahead and do that here. So my final piece of the puzzle here, let's interpret. So here's what we know. We know a prime of 9 is approximately, this is definitely approximation, -2 1/6. So first of all, let's just think about labels. Labels can go a long way sometimes in helping you interpret something. So what are these rates of change? They're changes in outputs over changes in inputs. So the change in outputs, kind of scrolling back up here to get our units, the change in outputs, this was volume in liters. So this was liters per, the change in inputs was change in time, and these were in units of hours. So a prime of 9 is the rate of change, the instantaneous rate of change at t equals 9. Now, 9, in practical terms, this was t equals 9, and this was the number of hours, and I need to scroll back up, after 7 a.m. So this is the number of hours after 7 a.m. So that means we're going to be at what? 5 hours later would be at noon. And so another 4 hours puts us at 4 p.m. Okay, so this then means we are at 4 p.m. So at 4 p.m., the derivative, so again, if we think about what does this derivative mean? So this is our instantaneous rate of change. Now, we don't know it exactly, we're approximating it. So instantaneous, which I'm spelling wrong here, instantaneous, I don't know why that looks weird. So our instantaneous rate of change. So our instantaneous rate of change at 4 p.m. is approximately -2 1/6 liters per hour. So let's again just kind of pull some of this thinking that we have here together, and then we're going to write out a much better kind of concise statement at the end of this whole discussion here. So as we pull this together, so let's think about this. So the instantaneous rate of change, and it's the rate of change in the volume, okay, at 4 p.m., so the instantaneous rate of change at 4 p.m. is approximately, negative means we're losing, 2 1/6 liters per hour. So let's pull this all together, but just in a little nicer language. So here's how we might say this. We might say, I like to start with at the point of interest of the problem. So I like to start with at 4 p.m. So this is an approximation, but not for any other time. This is our approximation for what is happening at 4 p.m. So at 4 p.m., now this instantaneous rate of change, well, what are we talking about here? We're talking about the volume of the tank, and that it's this tank full of water that's emptying. So writing this out in a little more practical terms, we might say the tank, or maybe even the volume of water in the tank. So the volume of water in the tank, so kind of describing what the function is in practical terms, is, and because this is negative, it means it's emptying, which we already had described to us in the problem, but even if it wasn't, we would kind of know it from the negative. It's emptying at a rate of, so here's my instantaneous rate of change, and it's emptying at a rate of about, this is our approximation, 2 1/6 liters per hour. And that's important. Like, we're going to do a lot of interpreting of derivatives this semester, and starting to get this interpretation down is important. So at 4 p.m., at the point of interest of the problem, the output of the original function in practical terms, so the volume of the water in the tank, is at this point being depleted, it's decreasing, it's emptying at a rate of, and so in this case we have an approximation of about 2 1/6, and there's our label, liters per hour. And that's kind of how you'll always label your derivatives. It'll be this output label per input label of the original function. All right, so next time, that's our last example I'm going to talk about in, formally at least here in 2.1. So next time, what we're going to take a look at is a different definition of the derivative, but this time, rather than it being the derivative evaluated at a specified point, it's going to be the definition of the derivative as a function. And so that's, here we've been always talking about the derivative, like even in this example, at a specified point. Next time we're going to talk about it more just as a function, like an a prime of t, let's say, rather than a prime at 9. So that's where we'll pick up next time.